applications start with ingestion. They take your text, break it down, and convert it into numerical coordinates called vectors. As you can see in this visualization, a chaotic sea of raw data points gets mapped into a vast, organized constellation of meaning. If you ask a question, the algorithm simply locates the nearest mathematical points. But a real user almost never asks a simple question. They don't want similar documents drawn from the entire database. They want similar documents within a very specific boundary. Only files created last week. Only records tied to their personal account ID. Adding that simple boundary constraint triggers a severe architectural flaw deep inside the system. Software engineers call it the filtering problem. When an AI suddenly drops a crucial source or hallucinates an answer, the language model itself usually isn't broken. The database sitting underneath it is tearing itself apart trying to reconcile two conflicting demands. The root of the problem lies in how data is stored. Fast vector similarity relies on one specific type of data structure, usually an HNSW index. Metadata filtering relies on a completely separate structure, like a traditional B-tree index. Look at this diagram. The web-like vector graph is completely disconnected from the rigid metadata hierarchy. When a query demands both, you force the two structures together. They clash. The vector index knows nothing about metadata, and vice versa. They cannot run simultaneously. The database has to guess which path to take. If it guesses wrong, it either silently drops highly relevant documents from your results, or its retrieval speed grinds to an absolute crawl. Anyone can build a prototype on their laptop that searches a few PDFs. Resolving this invisible tension is what separates a weekend project from an enterprise-grade AI system. Every database builder attacks this collision differently. Let's start with pgvector, an extension that lives entirely inside an existing Postgres setup. Look at this diagram of pgvector's strategy, known as post-filtering. It searches the vector index first to catch a large array of candidates in the top of the funnel. Only afterward does it apply the metadata filter at the very bottom. That works if your filter is loose, but if your filter is strict, say isolating a single user's private data out of millions of rows, the top vector results mostly fail the test. The database hits a wall and stops, silently under-delivering the documents your AI needs. ChromaDB takes the exact opposite approach to guarantee accurate results. It runs a pre-filter using a standard SQL database. The mesh moves to the top of the funnel, isolating only the correct data points before the vectors are ever searched. But by pre-filtering, Chroma bypasses the vector index completely. It forces the database to run brute force linear scans across the remaining files. At scale, that SQLite metadata step becomes a severe bottleneck. pgvector and ChromaDB prioritize operational ease. The trade-off is an architecture that struggles to support thousands of simultaneous users with strict data boundaries. For high-demand environments, you have to look at systems engineered from scratch to bypass the filtering clash entirely. Qdrant is one of those heavyweights. Qdrant tackles the problem through filtered index traversal. Instead of keeping the metadata and vector indexes isolated, they were co-designed to communicate. In this diagram, you can see how that communication pays off. The system evaluates the metadata filters first, instantly mapping which nodes are valid. During the actual search, the query intelligently skips over the inactive nodes, plotting a highly efficient route through the exact data you need. Then there is Pinecone, the fully managed cloud database. Pinecone solves the bottleneck by avoiding the clash altogether, relying on a concept called namespaces. Namespaces act as hard partitions at the index level. They physically separate tenant data. If you place each user's documents into their own isolated namespace, the search algorithm never even sees the rest of the database. The filtering problem never happens. These purpose-built systems survive enterprise workloads because they physically alter how data is isolated and evaluated before the search even begins. There is one more approach that takes a radical departure from everything we've discussed so far. LanceDB is built on a columnar storage format. Look closely at this data layout. Most databases store a document's metadata and its vectors side by side in horizontal rows. LanceDB dissolves that row structure. It stores all the metadata in one column and all the vectors tightly packed together in another. Keeping the vectors mathematically adjacent in memory unlocks massive compression rates. It allows modern processors to run SIMD instructions, single instruction multiple data, meaning the CPU can calculate similarity across multiple vectors in a single processor cycle. This architecture brings data lake features directly to machine learning workloads. You get robust versioning and the ability to query past iterations of your dataset natively, all without needing a dedicated server. Maximizing compute efficiency isn't strictly about rewriting search logic. Sometimes it demands physically reshaping the memory layout itself. This struggle between metadata and vectors highlights a recurring engineering choice. General-purpose retrofits prioritize staying within your existing stack, while purpose-built systems prioritize the specific bottlenecks that occur at scale. For prototypes and early-stage deployments, it is perfectly fine to rely on accessible tools like pgvector or ChromaDB. But you have to design your AI with a pluggable vector store abstraction layer. All of your retrieval code must flow through a standardized interface. As your application scales to support complex permissions and multi-tenant architectures, that initial database engine will break under the strain. The architectural choice you make today isn't permanent, but the penalty for getting it wrong depends entirely on your system's ability to seamlessly swap its engine when the invisible bottleneck strikes.